When talking about acids and bases, there's a good chance that at some point you've heard the term pH used before. In a context outside of this class, right? Like you may have heard about it in a previous science classroom, or even just something like the pH of pool water or something like that. And you may have some idea that this somehow refers to how acidic or basic something is. So the way that works is that, let's say we have a value for H3O+. For example, let's say we have an acidic solution where the H3O+, or hydronium ion concentration, is 2.4 times 10 to the negative 3 molar. That's the concentration of H3O+, but there are other ways to present this information that may be a bit easier to work with. So the term pH, this P right here, stands for the negative logarithm. And then it's negative logarithm of whatever's after the P. So in this case, the H stands for H+. So the negative log of the H3O+ concentration is what we get when we have pH. So in this case, the pH of this solution would be the pH of the negative log of 2.4 times 10 to the negative 3 molar. So we take the negative log of that number, and when we do that, we're going to get that this solution would have a pH of 2.62. Now, what this means is that our solution would be an acidic one. We specifically define that pHs that are less than 7 are acidic, and pHs greater than 7 are basic. So this scale gives us an easy way to talk about whether a solution is acidic or basic. And it's an easier way to present this information sometimes. Like the pH of something is 4.3 is easier sometimes than saying the concentration version. So let's do one other. Let's say I have a solution where the H3O+ concentration is 2.74 times 10 to the negative 10th molar. If I want the pH of that solution, I take the negative log of 2.74 times 10 to the negative 10th. Okay, so we go through and we do that. And when we do that, we're going to get that the pH of this solution is 9.57 now. Now this solution would be basic then, because that pH is greater than 10. Greater than 7. It's close to, it's 9.5. It's getting towards 10. So this solution would be a basic solution. Now, this information can be found, we can go the other way too. We can be given a pH and use it to find the concentration. This will be helpful if we need to know this concentration, for example, to use inside an ice table to try to solve a problem, or maybe we need to put this concentration into an equilibrium constant somewhere. Sometimes we know the pH, but we need our other value, our concentration of H3O+. So let's try it this way. So let's say we're told the pH of a solution is 8.2, and we're asked to find the hydronium ion concentration. Well, we said that pH is the negative log of H3O+. We can also rearrange this using what we know about logarithms to find 10 to the negative pH is equal to H3O+. So that means in this case, if we take 10 to the negative 8.2, and we get a value for that, we will get that a solution with a pH of 8.2 has a concentration of 6.31 times 10 to the negative 9 molar for its H3O+ concentration. So we're able to go both directions. We can be given a pH, find its H3O+, or given the H3O+, and find a pH. So that's how we go back and forth with those. Now, when we talk about this, you'll notice we mentioned acids and bases are relevant in this section, but this is only so far dealing with the H3O+. So what do we do about the OH-? Well, there are two ways to deal with this. So the first is that we'll deal with the fact that water autoionizes. So what the heck does that mean? So if you take two water molecules together, they will be in equilibrium with the process where one of the waters is a proton acceptor and one is a proton donor, and so generate an H3O+ and an OH-. In all our acid-base reactions we're working with, this equilibrium is also true because all the times we're talking acids and bases in this general chemistry course, we're going to be doing this inside of water. As a note, depending on what topic you're working on in school, you will have situations where you deal with acids and bases when they're not in aqueous solutions, and then this wouldn't be relevant. This is only relevant as long as there's water present, but for every acid or base we look at in this course, we're going to have this be true. So this equilibrium is going on back and forth. So we have to deal with that. And so at 25 degrees, we know that Kw is equal 1.0 times 10 to the negative 14th. And specifically at temperature of 25 degrees Celsius. The majority of questions we work on, this is a true statement. It's also just practically true. We do a lot of our reactions at room temperature. So as long as we're at room temperature, this is the value for Kw. You can find other values for it at other temperatures. It would be something that if you were doing a reaction not at 25 degrees Celsius, especially if it was particularly elevated or particularly low, you would need to look up a value for Kw at that temperature, or you could be given information to solve for it. But what this means is that if we're at 25 degrees, H3O plus times OH minus will be equal to 1.0 times 10 to the negative 14th. This is because, remember, in our equilibrium constant, we're going to write our aqueous ions, but we're not going to write our liquid ones. So we have products over reactants, but both reactants in this case are liquids, so they're not going to show up. And it's the same thing. So it would be H2O squared, but it's a liquid, so it doesn't show up there. So we just take the two concentrations and multiply them by each other. That means if we know one of those concentrations, we can find the other because they're connected via this equilibrium. So let's take an example with that. So if our hydronium ion concentration is equal to 1.9 times 10 to the negative fifth, what is OH minus? Anytime you know one and the other, you can connect them via Kw. So in this class, if the problem doesn't tell you otherwise, assume we're at 25 degrees Celsius. So Kw is H3O plus times OH minus, and you are expected to memorize this number for Kw at 25 because we use it so much, is 1.0 times 10 to the negative 14th. For this specific problem now, I want to find OH, so I'm going to divide both sides by H3O plus. When I do that, it'll cancel out on the left side, and I'll be left with my hydroxide ion concentration is equal to 1.0 times 10 to the negative 14th divided by H3O plus. Well, now we can plug in our numbers. So we have 1.0 times 10 to the negative 14th. In this case, it is divided by 1.9 times 10 to the negative fifth. So 10 to the negative 14 divided by 1.9, 10 to the negative 5. And we get 5.26 times 10 to the negative 10th. This is our hydroxide ion concentration. So if you know one, you could find the other. So we have H3O plus and OH minus. Now, let's go back and relate these two values then to how we know whether something is acidic or basic. I said in passing at the beginning of this video that when pH is less than 7, we're acidic. Now, what this means is that the H3O plus concentration, I'm trying to make a bracket there, not a 7, is greater than the OH minus concentration. This comes from that relationship of Kw. So at a pH of less than 7, what that means is that H3O plus is going to be greater than 1.0 times 10 to the negative 7 molar. And when you plug that value back into Kw, whatever value it is, as long as H3O plus is greater than that, OH minus is going to give you some value that is less than 1.0 times 10 to the negative 7th molar. So this is why 7 is that dividing line between acidic and basic. And that statement is only true at exactly 25 degrees. So if we're at another temperature, this starts to vary some, that the ranges won't be the same for acidic and basic. But if we're really close to 25, it won't vary a ton. But as you get further and further away, it changes more. This is why this scale works. We're going to talk about the scale mostly at 25 degrees, and most of our intuition will be built there because that's what we tend to work at. Tend to work at room temperature or really close to it, so that's where this relationship is true. Then you have the other case where pH is greater than 7, which is our basic condition, which means that our hydroxide is going to be greater than our H3O+. And that means we have the inverse of the relationship on the left, which is the H3O+ will be less than 1 times 10 to the negative 7th molar. And that OH- will be greater than 1 times 10 to the negative 7th molar. The most important part here is you should be able to be given an H3O+ or an OH- concentration or a pH. Any of those three pieces of information, and you should be able to be asked, is this solution acidic, basic, or is it neutral? Which is what we get at our pH equals 7. And you should be able to tell that. Also, from a practical perspective, when you get really, really close to 7, your solution behaves a lot like it's neutral. So if your pH is 6.85, that is technically slightly on the acidic side. And for the purposes of like test question-oriented things, I will be very clear. If I want you mess up these acidic, basic, or neutral, it will be 7 if it is neutral. But as you get really close to 7, it behaves a lot like it's neutral. It's not very strongly acidic. But as your pH starts getting lower and lower, it becomes more and more acidic. You take something like pH 3, and that's going to be a pH of, well, lemon's more like 2.2 or 2.5. And so I'm trying to remember all my numbers for it. So pH 3 is starting to get acidic. A lot of your fruits are going to be in that area. We have a lot of foods that are in that. I think sodas, like Coca-Cola, is around 3. As you get closer to pH 2, you're around the pH of like lime, like lemon or lime. And then you get down to pH 1. Your stomach acid varies from like 1 to 3, but that's like the most acidic that's going to be. And then as you get further down, it gets more and more acidic. Now with that, sometimes these numbers don't sound all that different, so it's important to have some points of reference. So like if I say something is a pH of 4 versus a pH of 2, at one level, that doesn't sound all that different. That's a difference of, well, literally 2. So what does 2 mean, though? It's important to remember that this is a logarithmic scale. Wow, I'm going to spell logarithmic correctly. There we go. Now, if it's a logarithmic scale, that means that every single point different is a jump of 10. So when comparing a pH 2 to a pH 4 solution, there's a difference of times 100 more H3O+ for the pH 2 solution. So that's important to remember that changing a single pH unit is a jump of 10. So if you went down to pH 1, that would be 10 times more concentrated. pH 0, 10 times again. And then pH -1 would be 10 times beyond that. So as you do this, remember these moves as you get further towards the extreme ends, either really, really low for high H3O+, or you get really high numbers like pH equals 12 versus pH equals 14. Now we're looking at where we're getting towards the basic side of it. So as we do that, every time H3O+ goes down, OH- goes up. So this means this here is going to have 100 times more OH- than this one. On the other side, it is true also the H3O+, that the one on the left is going to have 100 times the H3O+, compared to the right side, which will have less H3O+. So you can't have one go up without the other. So because the autoionization of water keeps these two these two things connected, the H3O+ and the OH-, if one goes up, the other goes down. I mentioned pH. We have some other scales using this P terminology. We won't use them as much, but you can also say pOH. So that means the negative log of the OH- concentration. So we can take, for example, let's say OH- equals 2.5 times 10 to the -3 molar. Then its pOH value is equal to the negative log of 2.5 times 10 to the -3. And when you do that, put that in my calculator real quick, and we will get that its pOH is 2.60. So you can talk about a pOH just like you talk about a pH. Both are things you can do. Another thing that's nice here is that because of Kw, as long as you're at 25 degrees, pH plus pOH together equal 14. So you can very quickly transfer between the two. So if I instead wanted the pH of this solution, but I had the pOH, I could simply plug into this equation. And we know that pH equals 14 minus pOH. Subtract it from both sides. So 14 minus 2.6. And when I do that, I will get a value of 11.40. So the pH of my solution is 11.4, which, as you remember, was a value that is basic, which makes sense. This OH minus concentration is larger than 1 times 10 to the negative 7th. So the pOH is going to be low when it's basic. The pH is going to be high. The inverse is true for acids. So when the pH is low, the pOH will be high. So we're going to use this as a unit of measure to talk about what the concentrations of these are. Different components, you want to be able to switch between them. Now finally, I'll mention that we can use this P for other things. So let's say we talk about something called pKa. So as a reminder, Ka is the acid dissociation constant. So that'll be HCl plus times A minus all over HA. So these Kas, you'll notice, though, have values that work well with the logarithmic scale as well. So let's say I take an unknown acid, and I find out its Ka is 2.7 times 10 to the negative 5th. Then its pKa, remember that P just stands for negative log. So I can do a negative log of anything. So we'll do the negative log of this. So you take the negative log of 2.7 times 10 to the negative 5th, and you get a pKa of 4.57. So you're able to do this as well. And you can do the inverse. 10 to the negative pKa is what the Ka is equal to. So we have 10 to the negative 4.57. You will similarly get that it is 2.7 times 10 to the negative 5th. This can be helpful in a couple of instances. We will have an equation later on in the course that uses pKa in it. Also, sometimes when you look up values for the Ka of an acid, you may get a pKa instead. And when you get that, you want to be able to convert back to a Ka because I need the Ka value so that I can use this as an equilibrium constant. So you should be able to go back and forth with it as well. So this P thing isn't just for pH and pOH. You can also do pKas. And we can use P for other things as well. It just stands for negative log of whatever comes after the letter P. So with that, I hope that helps with working with how we're going to deal with concentrations of the hydronium ion and the hydroxide ion. Following from this, we'll start to talk about now how do we get things like the pH of an acid, whether it be a strong acid or a weak acid, or a strong base or a weak base. So that's what we'll be going with next. And we'll be using all these concepts here to cover that. So I hope you have a good day.